calculator for this. All right? We're going to go ahead and do ideal and limiting reactant stoichiometry, hopefully all today. I'm going to tell you, this is something that usually takes, like on the instructional plan for honors, it's scheduled for a month. It takes us a month to teach it to them. We're going to do it with you in a day. All right? And that's, relax, it's not so bad. That's because you guys I wouldn't say that. You guys are sadomasochists, first of all. But number two, most of you guys are in pre-calc. You've had someone teach you dimensional analysis before. This is just a lot more dimensional analysis, but now we're throwing in chemical reactions. All right? Okay, so we're going to start with one particular chemical reaction. All right, so you know on the quiz today, you guys had that reaction with peroxide? Yeah? So first period complained about that because they're like, well, we don't remember that reaction. We don't remember the formula for peroxide. All right, so that particular reaction is one of those reactions, like when we get to kinetics, that's the reaction that I'm going to focus on daily. All right? It's a characteristic classic reaction that you're going to see it so frequently, you're going to commit it to memory. So is this one up here on the top of this paper. The equation that's here on the top of this paper is something called the Haber process. The Haber process is how we make ammonia from nitrogen and hydrogen. First of all, for us to do stoich, you need a properly balanced equation. That's not it. I left some blanks. Let's fill it out. So how do we balance this equation? 3 where? In the hydrogen? 1, 3, 2. 2NH3. All right, so number 1, besides obeying the law of conservation of matter, why do we balance chemical equations? What do the coefficients mean?
Figure out how many moles we need.
Oh, yeah, you're putting the cart before the horse. What do those numbers mean? The ratios and how much, right? So if, to the untrained eye, right, if they were reading that equation, they would say that what it says is that you need 1 molecule of nitrogen, right, to react with 3 molecules of hydrogen.
How would you get that to happen? Like if you have 1 single molecule.
That's the point I'm trying to make. And so from those 2 things, you make 2 molecules of ammonia. And so Jacob brings up a great point. First of all, how do you get 1 molecule to react with 3? And number 2, like, are 2 molecules of ammonia sufficient to do anything with? And 2 molecules is not enough. We have to be able to scale up this recipe. All right? And so that's what the mole lets me do, is it lets me scale it up. All right? So for question number 2, they ask, what units are the coefficients in? Well, it could be molecules, but I think what's more appropriate for something that you can hold in your hand and touch and feel and see is mole, right? So those coefficients really are in mole. All right, so let's take a look at a question like 3A. We'll do 3A together, and I'll leave 3B up to you to do. All right? 3A says, use dimensional analysis to solve the following problems. All right, so it says, if you need to produce 1.95 moles of ammonia, how many moles of hydrogen would you need to get the reaction started? All right, so I'm going to draw my fence post. What goes here? What goes here? 1.95 moles of NH3. All right, fantastic. What do they want? Moles of H2. So I'm going to write that over on the far right. All right, my dears. You don't have to know anything about how to do this besides how to do dimensional analysis. So what unit goes down here in this conversion factor? Moles of NH3. Why? I want this to cancel out with that. What unit goes on top? Moles of H2. Where do I find out this relationship? Where from the equation? From the coefficients, right? What does the equation tell me? For every 3 moles of hydrogen, how many moles of ammonia will I make? 2. All right, so if I didn't have my calculator handy, if I had to do this in my head, I would round that up to 2, right? 1.95 is close enough to 2. And then 2 times 1.5 is 3. All right? 3 moles. But I do have my calculator handy, right? So if I did have my calculator handy, I would go ahead and do it correctly to the correct number of significant figures. It's really 2.93 moles of H2. All right? And you want your answers to be consistent with the number of sig figs in the given. All right? Okay. We're not going to do B. I'm going to leave that up to you. Let's look at the question, because I want to make a point. It says, if you were given 7.3 moles of N2, how many moles of NH3 can you produce in theory? Is it the same relative idea?
Yeah.
Okay. The conversion factor that you used in both parts of question 3 is called a mole ratio. I'm going to highlight that. That's a vocab term we need to know. 6 mole ratios can be derived from the equation above. What do these mole ratios allow you to do in practice? Not always what I can make. Raj? Is it always about how much you need to make the product? You could do these questions one of two ways, right? So let's think about this in terms of cooking analogies. Say I went into my kitchen and I opened up my cupboards and I saw that I had 3 cups of flour and 2 cups of milk. So if I know the starting ingredients, I could use these kinds of questions to figure out how many cookies I could bake with that, right? In my cupboard, I said. Right? All right. Now, could you do the question the other way? What if someone said, I need you to go make 5 dozen cookies? Could you start with how much product you want to make and go back and then calculate how many ingredients you need? So you can go back and forth with these problems. If you want to think of it in a more generic term, right? What mole ratios let you do is stop talking about substances, like numbers from the perspective of one substance, and start talking about it from the perspective of a different substance in that reaction. It lets you convert between substances in the reaction. In industrial settings, usually the calculation works backwards. So let me give you an example. So say, for instance, I work for Bayer, and I'm making aspirin, and Walmart comes to me and says, we want to order 1 million capsules. Right? I would do the calculation backwards. I would start with how much I want to make, and then figure out how much of the starting ingredients I need, so that then I can order them from the supplier and make my capsules. So in industrial settings, it's usually from the product, the calculation's done starting with givens for the product, working your way to the reactant, not the other way around. Okay, but it doesn't matter. You can go back and forth. You can go from product to reactant to product. It makes absolutely no difference. Yeah. Okay. It is. Okay, number 5. What units were the answers in question 3 left in? Moles. What if you wanted grams instead? Multiplied by the molar mass. So you would use the mole ratio in combination with that mole conversion chart that we used in the last worksheet. All right, so let's do a practice problem. It says, if you need to produce 1.95 moles of ammonia, how many grams of hydrogen would you need to get the reaction started? All right, so I'm going to do my fence post. What goes here? 1.95 moles of NH3. What does the question want? So I'm going to write that over on the far right just to remind me that that's what I want. All right, so I'm starting with one substance, but I'm ending with a different substance. Your first objective, look at your given. Make sure it's in the right unit to do any of this. Is it? Yeah, right? The unit that you want to be able to have in order to use the mole ratio is the mole. We're in the mole. What if you hadn't been given the number in mole? Then you would convert it. Right, by using that flow chart from the other day. You always want to make sure you're starting with moles so you can go to the mole ratio next. All right, so the mole ratio is going to have moles of NH3 on the bottom. It's going to have moles of H2 on top. What's the ratio? There's 3 hydrogens for every 2 ammonia. All right? Now, moles of NH3 cancel out with moles of NH3. I'm left with moles of H2. Is that what they wanted? No. One final step, they want it back in grams. So think about this conversion factor. What goes in the denominator over here? 1 mole of H2. And on the top, what do we have? Why not 1.01? Because it's diatomic, right? It's 1.01 grams off the periodic table for 1 atom of hydrogen, but the formula says H2. You got 2 of them, so double it. All right? So let's just do some quick math in my head without a calculator, right? So 3 over 2 is 1/2, right? 1.5. Correct? So 1.5 times 2 is 3. 3 times 2 is 6. So we've got about 6 grams of hydrogen. Let's be a little bit more precise since we do have the luxury of a calculator. Oh, okay, so the calculator says 5.91. Hey, I was only off by 9/100ths. Is that a big deal? Not really. Not on a multiple choice test when answer choice A is distinctly different from B, which is distinctly different from C and D. All right? Okay. What if the quantities given to you are in grams or some other unit? What should you do first, considering that the reaction coefficients are in mole terms? Always convert to mole. I could have given you a starting ingredient in liters if it had been a gas at STP, right? I could have told you you're starting out with 15 liters of hydrogen. Your first objective should have been what? Convert it to moles. And you know how to do that, right? How do you go from 15 liters of hydrogen at STP? Divide by 22.4. I could have said that you had 29 million molecules of hydrogen, right? You convert to mole. Doesn't matter what given you have. Convert it to mole first and then go into the mole ratio. All right, so let's do a practice problem. It says, if you need to produce 7.5 grams of ammonia, how many moles of hydrogen would you need to produce it? All right, so we're going to start with 7.5 grams NH3. Is that a good starting unit for a fence post? No. What's the first thing we should do? Change it to moles. All right, so to change it to moles, I would have to put grams of ammonia in the denominator so that the units cancel out. What unit would go on top? Mole of NH3. Notice that I always start with putting in words, and then afterwards I fill in numbers. All right? After I fill in the words and I figure out what cancels out, now I ask myself, what is the relationship between moles of ammonia and grams of ammonia? Well, for every 1 mole of ammonia, however many grams it is, I can figure out by looking up the masses off the periodic table, right? So I would take the mass of 1 nitrogen, which is 14.01, and add to it 3 times the mass of hydrogen, each one being 1.01. So that ends up being 17.04, right? That's another one of those molar masses that I have committed to memory. That's how frequently I use ammonia. All right? Yes, Dan? Yeah. Now that I'm a mole, how do I stop talking about ammonia and start talking about hydrogen? You use the mole ratio. All right, so the mole ratio over here is going to have what in the bottom? 2 mole of ammonia. What will it have on top? 3 moles of hydrogen. All right, so let's see, 7.5 times 1.5 divided by 17.04. I'm getting 0.66 moles of H2. Is that what you guys get? And if you look, if I cross out all the units that are catty corner, I'm left with mole of H2, which is what they wanted in the answer. All right? We'll leave B blank for when you have a moment if you want to try it on your own. All of the questions above are considered ideal stoichiometry questions. These are ideal because the solutions are based upon the assumption that one of the reactants is in an unlimited supply, and therefore you don't have to think about it at all. We identify these situations by looking at the number of givens in the question. In all cases, how many givens were present in all of these questions on the front of this page? 1 given. when you have one given, all you have to do is one fence post. That's why this isn't ideal. You only have a one-step problem. All right? Easy, right? Where things are going to get a bit sketchier now is on the backside when we deal with limiting reactants. Okay? I'm going to teach you two ways of doing it. The old-fashioned antique way that takes forever and you have to remember a lot of parts. And then the new and improved way, something called a Rice chart, which is the preferred method. If you did not learn how to do Rice charts in honors, learn it now, because when we get to equilibrium, all equilibrium problems are done with Rice charts. Okay? All right, so let's go. Let's go to the back. Same equation again. All right, why change things up, right? So what do we need, a 3 here and a 2 there? And a 1 there? All right, so let's take a look at question 10a. Now they're asking, what if you were given 5 grams of nitrogen and 12 grams of hydrogen? What number do you start your calculation with? Who knows? All right, I don't know, beats me. I can't tell that quickly. This question is an example of a limiting reactant problem. How many givens do you have in this question? 2 givens. All right, so let's detour for a moment because I want you to understand the concept of limiting reactants before we actually start doing it. All right, so limiting reactant problems are like sandwich recipes. Say you have a recipe for a sandwich and it calls for 2 slices of bread, 3 slices of ham, and 1 slice of cheese. If you had an unlimited supply of bread and cheese, but only 9 slices of ham on hand, how many sandwiches can you make? How many? 3.
Is that Kyle?
No. All right. What if you had an unlimited supply of bread, but only 9 slices of ham and 2 slices of cheese? How many sandwiches can you make now? 2. What's the limiting reactant? Yeah, it's the cheese, but what's the definition of a limiting reactant?
Something that limits how much of a product.
There's 2 definitions. All right, so it is an ingredient that limits how much product you make. There's a second definition and a bit more important definition. After I'm done making my 2 sandwiches, how much cheese do I have? None. It's the ingredient that runs out. Well, I'm giving you recipes where the combinations are always in like perfect integer things. You can't actually make like half a sandwich out of
Yeah, but like if you had one excess molecule.
it. If you've run out of the other ingredient that it needs to combine with, it's just going to sit there. Okay. All right. The reactant that's not limiting is called an excess reactant. Give a definition. What's an excess reactant? The ingredient that you have left over. All right, so for instance, in part B, right? So say I made my 2 sandwiches and all my cheese is gone. How much ham do I have left over? 3 slices. 3 slices in excess. How much bread do I have left over? Infinite supply. That's how much you have in excess. All right? All right. Okay, so let me show you how to do these problems. The old way and then the new and improved Rice way. All right, so we're going to go back to question 10a. What if you were given those 5 grams of nitrogen and those 12 grams of hydrogen and wanted to know how many grams of ammonia are produced? And what if you also wanted to know which reactant was in excess and by how much? How do we solve these problems? So first, I'm going to show you the long way. This part, just put your pencils down and watch. You can always copy this down in a moment. Right? All right, so you have 2 givens. So what I was taught was if you have 2 givens, you do 2 fence posts. 1 given, 1 fence post, 2 givens, 2 fence posts. So you set up two fence posts. Solving for the same substance in the same unit. All right, so, okay, my first fence post will start 5.0 grams N2. The second one will start 12.0 grams H2. And if I read the question carefully, and I'll zoom in so you can see this a little bit better. The question says they want to know how many grams of NH3. I may as well just set both of them up solving for grams of NH3. All right, and I want these two to be solving for the same thing because I'm going to end up comparing these answers to another. And you can only compare apples to apples, right? Is that a unit that I want to see at the beginning of a fence post? Do you start stoic with grams? No. To start a stoic problem, what unit do you need? Moles. First thing I'm going to do is I'm going to change these to moles. So 1 mole of nitrogen weighs 28.02 grams. 1 mole of hydrogen weighs 2.02 grams. All right, so the first thing I'm going to do is change it to moles. Okay, next. Now I'm going to go into the mole ratio. According to the mole ratio, there's 1 mole of N2. And for every 1 mole of N2 that I use, I produce 2 moles of NH3. Down here, the mole ratio is going to look a little different. It's going to have 3 moles of H2 on the bottom, but it will still have 2 moles of NH3 on top. All right? Did we want the answers in moles? What do we want them in? All right, so let's go one more step to the fence post. 1 mole NH3 on the bottom, 1 mole NH3 on the bottom of both fence posts, 17.04 grams of NH3 on top, because to convert from moles to grams, you use that molar mass off the periodic table. Right? So cross out, we're in grams. All right, so if I do the first question, all right, so on my calculator, I'm going to do 5. What you do is you multiply all the numbers along the top, you multiply all the numbers along the bottom, you take the product of the numerator and divide it by the product of the denominator. So I'm going to do 5 times 2 times 17.04 divided by 28.02. I get 6.07 grams for that first question. And then for the second one, it's all right, not a big deal. I get 67.5. You don't even have to worry about the 08 because your original had 2 sig figs. I really should have written 6.1 anyways. Okay? All right, so step 2. We're going to throw out the extraneous solution. All right? One of these solutions is extraneous. What does extraneous mean?
Like, doesn't fit in.
It's wrong, right? Which one is the extraneous one? It's the larger one. All right, so I got 6.1 for the first one. I got 67.5. Which one's larger? 67.5? Throw it out. It's extraneous. Wrong answer. Okay? The answer is 6.1 grams of ammonia. All right? Now we're going to identify the limiting reactant. Okay? The limiting reactant is the substance that started that fence post, the correct one that we kept. Okay? So identify LR by looking at given from fence post you kept. All right, so what's my limiting reactant according to this? Nitrogen. All right? So let me write the equation down here so you can see it one more time, because it's up here at the top of this screen and you can't see it. So N2 plus 3H2 yields 2NH3. So we just said nitrogen is my limiting reactant. I'm going to abbreviate LR so that I know that that's it. Okay? All right, so then what's the excess reactant?
Hydrogen.
Hydrogen. All right? So I'm going to abbreviate that ER. I'm going to label that. People tell me, I've had people tell me that NH3 is the excess reactant.
No, we want that. That's a product.
That's a product. All right. Okay. All right. Reactants are only on the left side of the arrow, right? Okay. If it's not limiting, it's excess. All right. So from this point on, every calculation that you're going to do, because what they want us to know, we already answered the first part, but we didn't answer the second part, like which reactant was in excess and by how much. We know who the excess reactant is, but how much? Every calculation from here on out will start with a given for the limiting reactant. Okay? And so what we're going to do is, I'm going to do one more fence post, 5.0 grams N2, and I'm going to set it up and solve it for grams of the excess reactant, which is H2. All right, so step 4, all right, do a fence post. Okay, start with given for LR. I'm running out of room here. Solve for ER. All right, so it's going to start 5.0 grams N2, I'm sorry. I'm going to change that to mole because grams is no good, right? So I'm going to divide by 28.02 grams off the periodic table. Now I'm going to do a mole ratio. The mole ratio is going to have 1 mole N2 on the bottom. It's going to have 3 moles H2 on top. All right? And now I didn't want it in moles, I want it in grams, so 1 mole H2 is 2.02 grams. All right? Okay, so 5 times 3 times 2.02 divided by 28.02. I get 1.08 grams, 1.1 grams of H2 because I needed to 2 sig figs like my given. All right, so this is how much was consumed. Did they want to find out how much hydrogen was consumed? Is that what they wanted? No. What do they want? How much is in excess? And so step 5, where I need a little bit more room, you're going to subtract answer from step 4 from ER given. All right, so I used 1.1 grams of hydrogen, but is that how much I was given? How much was I given? All right, 12.0. Mr. Naughty. I'm an AP. Yes, I can. All right, bye. All right, so we've got 12.0 grams of H2. We're going to subtract from that 1 grams of H2 what I used. How much do I have in excess? 10.9 grams H2 left over. All right? That sucked, didn't it? Yeah. Jesus Christ. Can I what? Can I make it bigger? Listen, Jesus Christ has nothing to do with this. Okay? You know what you have to do these questions? Be a sadomasochist and memorize all these steps. And are you going to really remember this on the FRQ when you're freaking out because you're doing a 3-hour test? No. It's not. You know where people really have a tough time? This part's not such a big deal, because if you think about 2 givens, 2 fence posts, throw out the larger answer, figure out who limiting is, that's as much as the honors kids are asked to do. You can do that, right?
Wait, so they're not even asked to do as much of us, but they take 30 times as many days?
What we don't ask them to do, listen, relax. What we don't ask them to do is this last piece, because this is where they get lost. So when we ask them now, like, how much excess is left over, they can do that third fence post, because after you figure out who the limiting is, every calculation starts with that. They can do that. But then figuring out that you set it up for the other reactant, they struggle with that. And where they really struggle is like what they do with this number. Like, they have a tough time figuring out that you subtract it from the given for that substance. It's just way too many steps, all right? And I'm not, like, digging on the honors kids, because AP kids have problems with this, too. It's way too many steps, way too many steps. So I'm going to show you a preferred way, and I don't have a ton of time. I only have, like, 5-6 minutes. I'm going to show you something called a rice chart, where you don't have to memorize all these steps. Or there's still 5 steps, but they're just a lot easier to do. Okay? All right, so RICE stands for Reaction Initial Coefficients End. RICE. And I would prefer for you to learn how to do this chart because you can answer all 3 of those questions with, you can kill 3 birds with 1 stone, right? You can figure out how much product you make, you can figure out who the limiting reactant is, you can figure out how much X is left over just by filling in this chart. And it's really easy to fill in. Minimal calculations too, and you're not going to have nearly as much work to do on paper for this. All right? So step 1, fill in the reaction in the first line. All right, so what was that balanced equation? 1N2 plus 3H2 yields 2NH3. And the other real reason why I want you to really learn how to do these RICE charts is because when it comes to equilibrium, this is going to save you. All right? Step 2, we're going to fill in the initial line in moles. The initial line are the initial quantities given. Okay, now, this is critical. It has to be in mole. The RICE chart only works with moles. All right, so how much nitrogen was I given in the question? 5.0 grams. How much hydrogen was I given initially? 12.0 grams. How much ammonia was I given initially? None. I haven't made any yet. This is before the reaction has occurred. All right, but is that what the chart really wants? What does it really want? Okay, so I'm going to divide that by the molar mass, 28.02. I'm going to divide this by the molar mass, 2.02. So we're going to change that to mole really quickly. All right, so 5 divided by 28.02 is 0.18. And then for the other one, 12 divided by 2.02 is 5.9. I mean, one more sig fig, 5.94. Okay, and this should still be 0. All right, next I'm going to fill in the coefficients line. We're going to do some algebra here. Okay? All right, so C in RICE charts stands for change. I want you to think about this in terms of coefficients instead. Look at what I'm going to do in here. What did I do? Where do these coefficients come from? The balanced equation. I put some x's in there. Why am I subtracting on the left and adding on the right?
You're taking away stuff and getting something out.
Right. We're taking away ingredients. We're making products in its place. All right? Step 4. This is the critical one. This is the one where people struggle with initially. All right? We have to identify the limiting reactant now. Okay. So this is what I'm going to do. I'm going to take the initial value, right, for the first substance. And I'm going to multiply it by the ratio of the coefficient of the second substance, the second reactant, over the coefficient for the first reactant. So it's basically just the given in that first box times 3 over 1. All right? It's just that number times that over that. All right? What do you get? So what's 0.18 times 3 over 1?
Yeah, that'd be
0.54. I ask myself, is 0.54 greater than 5.94, less than 5.94, or equal to 5.94? It's less than. So I'm going to draw an inequality. All right? So 0.54 is less than 5.94, right? So I'm just basically comparing this value to that one multiplied by the mole ratio. I draw that inequality between boxes because that inequality is an arrowhead. Guess what it points to? The limiting reactant. Who is the limiting reactant? Nitrogen's the limiting reactant. So what does that tell me about hydrogen? It's the excess reactant. All right, now, what do you know about the limiting reactant? Runs out, so you got 0 at the end. Step 5, this is where it all comes into play now. This is the fun part. The R line plus the I line plus the C line equals the E line. So the initial plus the coefficient equals the N line. We're going to solve for X. And once we have X, we can substitute back in and figure out the rest of these columns. So look at this column here. We said 0.54, what the number was in the I line, right? Minus the coefficient line, minus the C line, equals 0. How much is X? 0.54. All right? And so now if I want to figure out what goes in here, it's going to be 5.94 minus 3 times 0.54. And then over here, it's going to be 0 plus 2 times 0.54. I'm just substituting in for X and then adding those two lines together to get the bottom one. All right, so 5.94 minus 3 times 0.54, I get 4.32. This is in moles for this hydrogen. All right, and then for the other one, 0.54 times 2, this is 1.08 moles for this last column. All right, so what does this tell me? Let's interpret. How much ammonia do I make? 1.08 moles. How much hydrogen's left over at the end? 4.32 moles. How much nitrogen is left over at the end? 0 moles. What if the question wanted these answers in grams? There you go. That's how you use the rice chart. Do you think this is easier to remember than this hot mess above? A lot more. We just have to practice it. Okay? All right, you do have homework on page 113, questions 57 to 63 odd, 71, 73, 77, 79. Please have them done by Wednesday. We can practice this some more on Wednesday. For a little bit. How come? Yeah.